Okay. Okay, let's read the problem here. It says the circle is inscribed in a square as shown in the figure. The circumference of the circle is increasing at a constant rate of 6 inches per minute. Just from this information, we'll just start gathering information. We may not need it until later, but it's good to just start to gather some information here. It says circle is increasing at a constant rate of 6 inches per minute. Can you decide what variable that could be referring to? Good, right? Circumference, you see circumference, you see rate, you see inches per minute. So we'll call that dc over dt. Okay, I'll just put that up here. Okay, positive or negative? Positive because and we see that word increasing, right? Okay, so let's just put a plus here to indicate that we did make that check. We did confirm that we're deciding what the sign of that rate is. Okay, as circle expands, the square expands to maintain the condition of tangency. So circle will expand, the square is going to expand along with it, but it's still going to be touching all the sides, okay, at those points. Okay, a circle has a circumference of c equals 2 pi r, and area of pi r squared. So part A says, find the rate at which the perimeter of the square is increasing. Okay, before we can do anything with derivative, we have to come up with some sort of an equation. Okay, how would you define define the perimeter of a square? What does that mean? Yeah, sum of all the sides, right? Sum of all the sides. Good. Next thing is, well, we want to be able to create an equation out of this. Some of us may be thinking, well, let's just call this x, and I'll just say it's 4x. But we really want to take advantage of the variable given to us, right? If we can recycle the variables, it's going to be a lot easier to see the links here. So we have r. R is for the circle, but do you think there's a way for us to represent the square's dimension using r? What do you see? Okay, yeah, so what do you think the full length of the square would be? 2r, right? Looks like that the distance, the radius of the circle matches exactly with half the length of the square. Okay, okay, does that make sense? So we know each of the sides is going to be 2r. Okay, so what do you think the perimeter of the square would be? Eight r, right? Add up all the four sides, 2r each side. Okay, I think we're ready to find the derivative so that we're trying to find dp over dt, right? Rate at which perimeter is increasing. So let's go ahead and find the derivative. P becomes dp dt. Eight r becomes 8 stays, but r becomes, yeah, d over dt. Okay, so this will be a lot easier if we can just, plug in dr dt, but looks like they didn't quite give us dr dt. They did give us dc dt. So maybe there's a way for us to get that link. Well, we have our circumference and area equations. Why don't we just go ahead and find the derivatives, get all the calculus out of the way, and see where all the pieces could fit, right? So I'm going to, I know that this is the only value they gave us, and we have to find a way to make that connection because we don't have dr dt. So maybe it's going to come from one of these equations here. Okay, so let's backtrack here. C equals 2 pi r. Let's go ahead and find its derivative. Okay, what does C become? dc over dt. Okay, 2 pi r becomes good. There's no need for product rule. 2 pi just stays. R becomes dr dt. Okay. Maybe we don't need this, but let's just go ahead and get this out of the way too. A is pi r squared. We'll just go ahead and find its derivative just in case we need it. A becomes dA dt. Pi r squared becomes 2 pi r dr dt. Okay, so we're finished with all the calculus for part A. Is there a link for us to maybe get to this dr dt? What do you think? Good, right? So there's our link, right? We have the derivative that connects dc dt with dr dt. And if I have 6 plugin for dc dt, I can find dr dt. And if I have that, that will lead me to my answering part A. I'm trying to find the rate of change of perimeter. I'm trying to find this dp over dt. Okay, so we don't need this yet, but we'll just go ahead and substitute 6 in for dc dt. Divide both sides by 2 pi. So dr dt is equal to 6 over 2 pi, which reduces to be what? Good. And careful, right? I know pi seems strange in the denominator, but that's where it ended up, so that's where we're going to have to keep it. Hey, dr over dt equals 3 over pi. Let me just put that up here. Okay, it's not what we're looking for, but it is needed for our final answer. So now we're ready for our dp dt. Make that final substitution. Okay, what's our unit of measure here? Yeah, inches per minute. Okay, so just as a reminder, most of your units will be one-dimensional, except for area, which is unit squared, or volume, which is unit cubed. But like perimeter, circumference, radius, height, they're all just going to be one-dimensional unit. Okay. All right. Good. Any questions so far? Okay, part B. At the instant when the area of the circle is 25 pi square inches, find the rate of increase in the area enclosed between the circle and the square. Find the rate of increase in the area enclosed between the circle and the square. Okay, so that's these shaded regions here, right? We want to find the rate of change of the area. Now we see that these by itself are not geometric shapes, right? But maybe we can create an equation out of the geometric shapes that we do have. So how can we go about finding the area of these shaded region, generally speaking? Can we come up with an equation that will represent the area of the shaded region? Good, right? So These aren't geometric shapes, but they come from geometric shapes, right? We can take the square, subtract out the circle, and what's left are these remaining parts. Okay, so we're going to create that equation, and then we'll worry about the derivative after we have that equation in front of us. Okay, so I'll let A sub E be the area of the shaded region, area of the enclosed, is equal to the area of the square minus the area of the circle. Okay. We can fill these with variables and equate with the formula, and then we can worry about the ADT here, right? So area of a square. What's the area of the square using the variables that we've already kind of begun to establish here? What's the area of a square in general? Yeah, length times width. Can we use how would we do that using the variables we've already established? Yep, 2r times 2r. So that's 4r squared, right? Okay. Area of the circle, that's just pi r squared. Okay, so we can say area of the shaded region, area of that enclosed region is basically just 4r squared minus pi r squared. Good. We have everything in terms of the variable that we want. We'll just go ahead and jump into our derivative. We'll find dA dt of the enclosed region. So A becomes dA dt. 4r squared becomes 8r. What comes after that? dr dt, right? Minus 2 pi r dr dt. Okay. We're talking about the same scenario as part A, just a very specific point in time. So we can actually reuse some information we've already gathered from part A, dr dt, but what information are we still missing? We still need the measurement for what? Good. Okay, they don't tell us R directly, but what information is provided for us in the problem? Okay. At the moment in time, we're told that the area of the square is 25 pi square inches. Can that be helpful for us to find radius? Yeah, area of the circle, sorry, area of a circle is pi r squared, right? So if I use that connection, I can find the radius at that moment in time. Divide both sides by pi. 25 equals r squared, so r is equal to 5. Okay, I think we have everything now, right? We have radius accounted for, we have dr dt accounted for. We can find that dA dt now. Do a little bit of cleanup. Pi's can cancel out. 40 times 3 is 120. So I can get these to go away. 15 times 2 is 30. There's no need to find common denominators. It feels incomplete, but this is a numeric answer that's good enough. Okay. What's our unit of measure? Area is what? Time component per minute. Okay. Any questions there? So we always have to create an equation before the derivative can come into play, right? Here, you know, it's like, oh, I gotta find the rate of change of the area. How do I do that? We always have to come up with a geometric equation before our calculus can be applied. And then the second thing that is not tricky, but just unique about this problem is, using that radius in a way that can be applied to something other than the shape that it was designed for, right? Using that R radius variable for the square turned out to be very helpful, because if we use a different variable like X or L or W, we're stuck not being able to see that connection. But having that radius already tied in with the circle proved to be beneficial for this problem. Okay, also notice something that I want to point out is a lot of times on free response questions on AP exams, it's not always, but a lot of times if you're looking at parts A, B, C, and D, you're working through, they usually try to kind of layer the problem. They start, kind of building that foundation, and then they add more complexity to it. But a lot of times they also ask you to refer back to information that you can use from the previous part, right? So a lot of times there's that connection. Oh, I'm going to use information from part A or into part B, or part B for part D. So they always try to draw some sort of connection between each of the parts. So it's always good to kind of review and look back at what you found and see there's a way to connect. Okay, we're going to skip number 2 for now. Let's go to number 3. So I like this problem because it allows us to review 2 distinctly different related rates problems. We have cone, we have a cylinder. They both have very similar formulas, but they have very distinct ways that we handle them from a related rates standpoint. Okay, so let's read the problem. As shown in the figure above, water is draining from a conical tank with a height of 12 feet and a diameter of 8 feet into a cylindrical tank that has a base with an area of 400 pi square feet. The depth h in feet of water is changing at a rate of h minus 12. Volume of a cone with a radius r with height h is 1/3 pi r squared h. Part A just says write an expression for the volume of water as a function of h. So here it's basically telling you which variable to replace. It's telling us, okay, let's just get rid of r, and we're just going to get our volume equation in terms of h. Okay, but we know with cones that we have to build that relationship, right? We can't plug values in for r and for h for water in the tank because it's constantly changing. So you have to go through similar triangles. Okay, so let's see if we can do that. Let's see if we can practice building our similar triangle, building that proportion relationship, and then replacing r so we can get our equation in terms of h. So part A, no calculus involved. We're just getting that volume equation set up. And then when we get to part B, then it's going to begin involving derivatives. Okay, so I'm going to start off with a diagram and see if you guys can make some progress here. So I'm just doing a cross section of my cone here. Okay, what can I put up here? Good, right? They give us the diameter, so we have to make some adjustment here. Okay, radius of the small triangle is to the radius of the large triangle, or radius of the small cone is the radius of the large cone, as the height of the small cone is to the height of the large cone. All right, so from here, see if you can make the appropriate substitution into the volume equation and get your volume equation all cleaned up. Okay, let me just see how you guys do with that step. Okay, it's the most important step, I feel. This is the one that there's no calculus involved, but it's all the algebraic messiness that we have to get through. So if you want the radius, it's already up here. That's all. Nicely. So once you make your substitution, make sure that you're cleaning things up, distribute the exponent through, push all the coefficients numbers together, nice fraction, push all the variables together. We should only be dealing with h raised to an exponent. Get it all cleaned up. Yeah, that's good. Push the h on the process, and that's not wrong. I want to solve a bar. Solve the bar because you want the h's to be. So not yet, just multiply, just get all cleaned up. The derivative will come. Substitution. This, that's good. This, Okay, let me walk through each step here. Okay, so r over 4 equals h over 12. They're telling us to solve for, in terms of h, that means we want the r to disappear. So I'm going to solve for r here. Okay, divide both sides by 12. Four over 12 reduces to be 1/3, h over 3. Okay, so I'm going to take that and insert it into my volume equation. Okay, in terms of h, so that means I want this h over 3 to insert into the r variable. Okay. All right, does that step make sense to everyone? Okay. We do further cleanup. We want to expand this all the way out. The h and the 3 get squared. And we can further clean up, right? I can merge all the coefficients into one fraction. I can merge the h's together. So we don't want to stop here. We want to go a little further so that we will be nice and ready for part B when we're ready to find the derivatives. Okay, so all it's asking for from part A is for us to write an equation in terms of v and h with the radius replaced. All right, does that step make sense? Okay, so now part B, at what rate is the volume of water in the conical tank changing? So now we're looking for dv dt of the cone. Okay, so now we can move on to the derivative. Okay, so v becomes dv dt. Pi over 27 stays. H cubed becomes 3h squared. And don't forget dh dt. Okay, we have 3 in for h, but looks like part B doesn't mention anything about dh dt. Is there anything else in the problem where they tell us about maybe dh dt that we could use? What do you guys see? You see anywhere in the problem where they're maybe giving us information about dh dt? Yeah.
Maybe like when we did like r equals 4 12.
I think something in the problem though. Yeah, Drew.
The last word, like the last part of each word is 12.
Yeah, so right here, right? So it's kind of hidden in the description here. It says the depth h is changing at a rate of h minus 12. So, you know, we see that h, you see the word changing, so you know it's dh dt. It's a little strange because they don't give us a number, they give us a variable. But we'll just make that adjustment, and then we should still be able to get down to a number. So we should have to understand that is referring to dh dt. So I'll put that to the side here. We know dh dt is h minus 12. Okay, there's a formula that's not quite giving us the numeric value, but we can make that substitution, and then we should be able to make progress, right? Because we know what h is once we make that substitution. Okay. Okay, h is 3. Okay, and then once I put that h minus 12 in for dHdt, I'm also going to substitute h with 3. Three times 9 is 27. 3 minus 12 is negative 9. Okay, so a lot of things cancel out here. The 27 goes away. 3 minus 12 is negative 9. We keep the pi. Still part of our answer. Okay, what's our unit of measure here? Talking about volume here, right? So right, cubic feet. What's our time component? Per minute. Okay, so this is talking about the rate of change of volume of the water in the cone. Does that negative sign make sense? Okay. What's happening with the rate of water coming? What's happening to the rate of water inside the tank? Decreasing, right? Water is leaking out. Okay, water is leaking out. So this is the rate at which water is leaving the tank. Okay. Let me make some connection here. All we know is dV/dt for the cone. Do you think we know what the dV/dt is for the cylinder tank? It's the same amount of water leaving as it is entering the tank, right? So what do you think dV/dt is for the cylindrical tank? Be positive. Okay. So that is a slight adjustment we have to make when we get to part C. So just want to make that connection now. dV/dt for the cone is negative. The dV/dt for the cylinder is positive. The amount of the rate at which water is leaving is exactly the rate at which water is entering into from one tank to the next. Okay, now part C. Let y be the depth in feet of the water in the cylindrical tank. At what rate is y changing when h equals 3? So normally we would use volume equals pi r squared h for cylinder. But just so that we don't have a mixture of variables, repeated variables, they're using a to represent the radius and y to represent the height of the cylinder tank. Okay. And some water level here. All right. Is there any information that they provide for us about this cylinder tank? Another hidden information from the problem. What do you guys see? Okay. Anything else? Oh, y equals what? Okay. Anything else about the description of the cylinder? Yeah.
Has a base with the area of 400.
Okay. Yeah. So, some of this information is hidden in the description, so we have to kind of pull that. Base of the cylinder has an area of 400 pi square feet. What shape is the base of that cylinder tank? It's a circle. Okay, so area of a circle is 400 pi. So we have to use that knowledge now, okay? Okay, the base of the cylindrical tank is pi r squared. Now we can use that information to solve for r, and I know r is going to represent a. So let's do that. Divide both sides by pi. Take the square roots. We get plus or minus 20, but only 20 makes sense. Okay. The radius of the tank is 20 feet. Now, what do we know about the radius of the water level that is different than radius of a cone? It stays what? Stays as a constant value, right? We know it's not going to change, right? As water level is dropping or increasing, it's not like a cone where the radius is going to be rising or changing, increasing or decreasing because of the shape of the cone is allowing that to happen. Here, that radius is staying the same all the way through, which means that as soon as you know what the radius is, you can go ahead and substitute it. We should not have to hold on to that variable like how we do with cones. We got to go through similar triangles and find a way to get one variable in terms of the other. Here, if you know what the radius is, just insert it with a number, get rid of the variable. We're gonna have a much easier time with our derivative process. Okay, so we know that r is 20, which is really a for our what we define as the radius. We can go ahead and just replace that a at the very beginning, because we know that's never going to change at the beginning, middle, or end of the problem. Okay, if we read the problem here, it says, at what rate is y changing? So we're ultimately looking for dy dt, and I think we should have an easy path towards solving for dy dt, right? Now that we have a taken care of, the radius taken care of, we can find the derivative, okay? So v becomes, okay, dv dt. What does 400 pi y turn into? 400 pi dy dt. Okay, we're looking for dy dt. Do we have dv dt information? Carries over from part B, except what do? Make it positive, right? Water is coming into the tank. The rate of change of volume is increasing, not decreasing. Divide both sides by 400 pi. Pi's cancel out. Okay, what's our unit of measure? Feet per minute, yeah. We're getting a positive value in return, which is what we expect. We made that dv dt positive, which means that dy dt is also positive. Now, what information did we not even use from this problem? H equals 3. Now, this would have been perfectly useful for a cone, but not for a cylinder, right? Doesn't matter what the height is. It's not going to change the rate of dy dt, right? So looks like it's not going to play a role. It plays a role for cones, but not for cylinders. So sometimes we have some extraneous information that we don't even need to use. Okay, I'd like to start a little bit with a test review. So if we can go to next page here. Okay, this is a Pythagorean theorem problem. Let's go ahead and we're going to go ahead and draw this diagram here. A balloon is rising vertically above a level straight road at a constant rate of 1 foot per second. 1 feet per second. Just when the balloon is 65 feet above the ground, a bicycle moving at a constant rate of 17 feet per second passes under it. So at t equals 0, bicycle is going to pass underneath it, but eventually it's going to make its way further and further away from the balloon. How fast is the distance between the bicycle and the balloon increasing 3 seconds later? Okay, this is where the tricky part comes in, but we'll come back to this a little bit later. But we know it's a Pythagorean theorem problem, right? We have the distance from the starting point to the bicycle, that's x. We have y representing the rise in the balloon, and we have z representing the distance between the balloon and the bicycle. Okay, Pythagorean theorem, we'll go ahead and set up that equation. Okay, derivative. All the d over dt start showing up. Okay, we have all the variables sitting in front of us. Let's go ahead and give room for us to label them. Okay, balloon is rising vertically above a straight route at a constant rate of 1 foot per second. What do you think that is going to replace? Good, right? We know it's a time involvement. We see that for a second. It can't be one of these. It's a vertical movement, so dy dt. And why is it positive? Okay. Yeah, because y is changed. Y is increasing, right? That distance between the balloon and the ground is increasing. Okay. Just when the balloon is 65 feet above the ground, so we'll hold off on that. This is something that we got to be careful about. Let's skip that for now. Bicycle is moving at a constant rate of 17 feet per second. What is that for? Good, right? And it can't be x, right? We see time involved. It's a rate. Okay. Positive as well because it's going to cause x to increase. How fast is the distance between the bicycle and the balloon increasing? What are we looking for? Yeah, that's our ultimate goal here for this problem. Now, we have to figure out how the triangle looks 3 seconds later. Okay, let's talk about that for a moment. The bicycle is here at t equals 0, but it's going to end up here at t equals 3. How much distance has the bicycle covered in that time period? 17 times 3, right? He's moving at 17 feet per second, so after 3 seconds, he's going to cover 17 times 3, which is 51 feet. Okay. Now the balloon is 65 feet above ground at t equals 0. Is it going to stay at 65 feet 3 seconds later, though? Where's the balloon going to be off the ground 3 seconds later? Okay, why 68? That's right. 3 seconds has passed. 65 when the bicycle is right underneath it, but 3 seconds past, that balloon is still moving, right? It's going to keep rising 1 foot per second. 65 plus 3 is 68. Okay, so that's the tricky part. Tricky part is getting to that x and y because they don't quite tell us the value. They give us information that connects it, but they don't give us the numeric value. We have to kind of imagine the problem in motion and see how that plays a role. Okay. From here, Pythagorean theorem gets a z. Once we get to z, we can plug in and find dc over dt. Okay, so we'll finish this problem on Monday, and we're going to focus our attention to try to finish out the rest of this review packet. Okay, help session, 4th period lunch today and after school. If you can't make it, that's fine. I'll record it. But I'm just going to pick out problems from the previous worksheets, just more related rates problems, in case you want to come and check it out.
Are you doing any next week?
Yeah, help session Monday afternoon and Tuesday morning.
Got it.
Yeah.